learners, today we will continue with the chapter Polymers. During this session, we will be discussing about types of polymerization reactions, mechanism of these reactions, preparation of some addition polymers and their uses. We will also learn about preparation and uses of some condensation polymers. We will first talk about addition or chain growth polymerization. Here the molecules of the monomer or different monomers add together on a large scale to form a polymer. The monomers used are unsaturated compounds, mainly alkenes or alkadienes and their derivatives. This mode of polymerization, leading to an increase in chain length or chain growth, can take place through the formation of either free radicals or ionic species. The ionic species can be cationic or anionic in nature. However, the free radical governed addition or chain growth polymerization is the most common mode. In this session, we will focus on free radical mechanism only. The common examples of such polymers are polythene and polytetrafluoroethene, also known as Teflon. While condensation or step growth polymerization generally involves a repetitive condensation reaction between two bifunctional monomers. These polymerization reactions may result in the loss of some simple molecules such as water, alcohol, and lead to the formation of high molecular mass condensation polymers. In these reactions, the product of each step is again a bifunctional species and the sequence of condensation goes on. Since each step produces a distinct functionalized species and is independent of each other, the process is also called step growth polymerization. As shown here, the reaction of ethylene glycol and terephthalic acid to form terylene is an example of this type of polymerization. But in order to understand the chemistry of various reactions, it is important to learn about their mechanisms, and we will now talk about free radical mechanism. As shared earlier, it is commonly followed by reactions undergoing addition polymerization. A variety of alkenes or dienes and their derivatives polymerize in the presence of a free radical initiator like benzoyl peroxide, acetyl peroxide or tert butyl peroxide. Let us take the example of polymerization of ethene to polythene. I hope you all must be wondering that many concepts of polymers can be well understood with the help of example of polymerization of ethene to polythene only. Now, this reaction consists of heating or exposing to sunlight a mixture of ethene with a small amount of benzoyl peroxide initiator. The process of polymerization can be divided into three steps. The first step involves the addition of phenyl free radical formed by the peroxide to ethene double bond, thus generating a new and a larger free radical as shown in the equation, and this step is called chain initiating step. As this radical reacts with another molecule of ethene, another bigger sized radical is formed. The repetition of this sequence with new and bigger radicals carries the reaction forward, and these steps are termed as chain propagating steps. Ultimately, at some stage, the product radical formed reacts with another radical to form the polymerized product. This step is termed as the chain terminating step. The sequence of steps is well depicted here. Now, we will learn about mode of preparation, characteristics and properties of some important addition polymers. An addition polymer that is used extensively in our daily life is polythene. So, we will first talk about the properties of polythene, and there are two types of polythene termed as low density polythene and high density polythene. While low density polythene is obtained by the polymerization of ethene under high pressure of 1000 to 2000 atmospheres at a temperature of 330 to 570 Kelvin. This reaction is carried out in the presence of dioxygen or a peroxide initiator as a catalyst, and the polymer so obtained has highly branched structure. It is chemically inert and tough but flexible, and therefore, it is used in the manufacturing of squeeze bottles, toys and flexible pipes. It is also a poor conductor of electricity and is therefore used in the insulation of electricity carrying wires. When I talk about high density polythene, it is formed when addition polymerization of ethene takes place in a hydrocarbon solvent in the presence of a catalyst such as triethyl aluminum and titanium tetrachloride. The reaction is carried out in the temperature range of 333 Kelvins to 343 Kelvins and under a pressure of 6 to 7 atmospheres. You can very well see that how the temperature, the physical properties determine the type of the polythene that is obtained. In one case, we are using high temperature and high pressure conditions, whereas in the other case, the temperature is nominal and even the pressure is quite low. The polymer thus produced consists of linear molecules and has a high density due to close packing. It is also chemically inert and more tough and hard and is used in the manufacturing of buckets, dustbins, bottles and pipes. When we talk about other addition polymers, the other common one is Teflon, which is polytetrafluoroethene. It is manufactured by heating tetrafluoroethene with a free radical or persulfate catalyst at high pressures. It is chemically inert and resistant to attack by corrosive reagents and therefore finds its use in the making of oil seals and gaskets. Though Teflon coatings undergo decomposition at temperatures above 300 degree centigrade, these are quite frequently used for non-stick surface coated utensils, whereas the addition polymerization of acrylonitrile in the presence of a peroxide catalyst leads to the formation of polyacrylonitrile. It is used as a substitute for wool in making commercial fibers, as these fibers have good resistance to stain, chemicals, insects and fungi. The application of all these polymers clearly reflect their importance in our lives. Now, we will also learn about the mode of preparation and uses of some condensation polymers that are characterized by their linking units. The polymers possessing amide linkages are also called polyamides. They are important examples of synthetic fibers and are termed as nylons. Two important types of nylons are nylon 6,6 and nylon 6. Nylon 6,6 is prepared by the condensation polymerization of hexamethylene diamine with adipic acid under high pressure and high temperature, and this is shown in the equation. It is named so as it is made from two monomers, each having 6 carbon atoms, and it is used in making sheets, bristles for brushes, and finds immense application in textile industry. The other type is nylon 6, which is used in the manufacture of tire cords, fabrics and ropes. This is prepared by heating caprolactam with water at high temperatures as depicted in the equation. Similarly, the polymers possessing ester linkages are termed as polyesters. Terylene, which is also known as Dacron, is manufactured by heating a mixture of ethylene glycol and terephthalic acid between 420 to 460 Kelvins as represented in the equation. The reaction is carried out in the presence of zinc acetate antimony trioxide as a catalyst. The fiber of this polymer is crease resistant and is used in blending with cotton and wool fibers. It is also used as glass reinforcing materials in safety helmets. By looking at the varied applications of these polymers, it is very difficult to imagine our lives without them. As shared earlier, the oldest synthetic polymer is phenol formaldehyde polymer, and it belongs to the category of condensation polymers. It is also referred to as bakelite. This is obtained by the condensation reaction of phenol with formaldehyde in the presence of either an acid or a base catalyst, and it involves 3 major steps. The first step is the reaction starts with the initial formation of ortho and or para hydroxymethylphenol derivatives as shown in the equation. These derivatives further react with phenol to form compounds having rings joined to each other through CH2 groups as shown in the equation. This linear product is called Novolec, which is used in paints. Novolec on heating with formaldehyde undergoes cross-linking to form bakelite, and this polymer is used in making combs, phonograph records, electrical switches and handles of various utensils. While condensation polymer that is used in making unbreakable crockery is melamine formaldehyde polymer, and it is prepared by the condensation polymerization of melamine and formaldehyde. The sequence of steps in the reaction are depicted in the equation. Dear learners, let's summarize what we have discussed during this session. In the presence of an organic peroxide initiator, the alkenes and their derivatives undergo addition polymerization or chain growth polymerization through a free radical mechanism. Polythene, Teflon, Orlon are some important addition polymers. We have also learnt that condensation polymerization is shown by the interaction of bi or polyfunctional monomers. This type of polymerization proceeds through the elimination of certain simple molecules as water, alcohol. The condensation polymerization progresses through step by step and is called step growth polymerization. Nylon, bakelite and Dacron are some of the important condensation polymers. Before we end today's session, let me leave you with an assignment comprising of 4 questions. Question number 1. In 1963, Nobel Prize in Chemistry was awarded to 2 scientists for the development of the catalyst X. The polymer Y obtained using this catalyst consists of closely packed linear molecules? What is X and Y? Name a few properties and uses of Y. Question number 2. Outline the difference between chain growth and step growth polymerization reactions. Question number 3. What is the IUPAC name of the following monomers? Number 1, melamine. Number 2, acrylonitrile. Number 3, terephthalic acid. And number 4, caprolactam. Question number 4. Write the chemical reactions involved in the preparation of first man-made synthetic polymer. Dear learners, I hope you have understood the concepts taken up during this session and you will enjoy answering these questions. Thank you and take care.